This is the last lecture covering Chapter 3 of Computational Optical Imaging. Next episode we'll start talking about physical imaging systems by talking about geometric imaging, and we'll move on to waves and statistical imaging. So we've been talking about neural methods in the last couple of lectures, and obviously neural methods is an enormous topic that we won't fully cover in this course, but they're evolving rapidly. What you see here is something from 4 years ago, the neural radiance fields, which uses the implicit neural representation that we talked about in episode 8 to estimate three-dimensional objects from a few views. You capture a few views and then use regressive training to be able to interpolate views. This is just a novel way to represent three-dimensional data. So you see as the objects move, you're able to interpret new views. Now, as we've seen, multidimensional imaging is actually the core problem in computational imaging. This method will apply to other forms of multidimensional imaging as well, including hyperspectral imaging, video, and any form of radiance imaging of all different types. So this is very exciting and a different way for us to think of neural processing and part of a sort of landscape that we'll review today. Another recent development is this work on Gaussian splatting, which solves the same problem as NeRFs, but by using representations of data on a three-dimensional Gaussian splat that has a certain form. This is not really changing the way measurements are taken. It's changing the way we represent measurement data as we estimate objects. Rather than estimating pixel values of the objects, you estimate this Gaussian splat cloud that you can use to regenerate the data. Again, a very novel and interesting way to manage three-dimensional images. So today we're going to talk just about this landscape a little bit, and then we'll move on to talking about physical systems in the next discussion.
Computational imaging. Episode 19, Neural Processing for Computational Imaging. Chapter 3 has discussed various algorithms for image estimation from data. Now, computational imaging is about computation, which means we use software. Software basically today means neural processing. As we've seen in several examples, we can use AI to generate software very easily, and neural processing is more and more integral to the very nature of what software is. In this episode, we're going to talk about the various applications of neural processing in computational imaging and give some landscape for what may come from these kind of algorithms before we move on to discuss physical systems in the rest of this series. Now, this particular example is drawn from this paper from Nature Methods looking at super resolution in optical microscopy. So super resolution is kind of a misnomer because we have measured data and basically we're trying to decide how to display that data, and we'll always want to upsample the data from measurements. We'll talk about this topic in some detail in section 7.5, which is about 36 episodes from now. But what you see here on the left is measured data from a microscope. And then on the right, various methods for improving the resolution of these measurements. So you see the measurements are blurred due to the impulse response. This first column is structured illumination microscopy, so a physical super resolution technique by taking multiple frames with structured illumination. And sequentially, we have various strategies for super resolution from the blurred data. The first one is a convolutional neural network. The second one is EDSR, and pixel-to-pix and the GAN network are all more advanced versions of neural super resolution techniques, and you see that they improve the image substantially. And so certainly just using neural networks, as we did with the demosaicing network to estimate image data, is a fundamental and attractive use of neural processing. But other applications of neural processing in computational imaging include ways to think about representation of data. Now, earlier in this lecture series, I showed you this figure from this paper from Nature Communications talking about a physical layer encoding system, and we'll talk, as I mentioned in the last lecture, we'll talk in chapter 8 about decomposition of images onto feature spaces. And so this image on the right is an image from chapter 8 of a PCA analysis of a hyperspectral image onto its features. You can use neural networks to find the features that best describe an image, And so that's a second application of neural processing. And finally, a third application is neural control. And the most direct example of that would be using neural networks to control gameplay. So, neural networks can be used for optimization, and here we want a robot to decide what kind of move to take in a game. Certainly, like another example of that would be autonomous driving. So the car needs to decide what to do, and it'll use a neural control system to figure out what kind of movement to take. This same kind of learning, though, comes about in cameras. So anytime you work with a conventional camera, you see that you have all these buttons and dials and knobs to turn. All of that can be controlled by a neural network. And so in computational imaging, we can use neural processing to determine what measurements to make, what focus to set, what exposure to set, where to point a camera, and so on, how to set our parameters adaptively. So these three different applications of neural networks correspond to, again, image estimation, and in that case, the neural processing is called supervised learning. And then we have the definition of what we want to do with supervised learning is we have a known ground truth that we want to achieve in an imaging system, which would be this y sub I or y sub I hat, and then we're going to relate the error of our estimated scene to the ground truth image, and we train the network to minimize this mean square error between the ground truth and the known image. Now, the second one is we have a feature estimation. We're trying to find underlying features, and these features may not be known a priori. This is unsupervised learning, where we want to find the structure in data without knowing the ground truth value. In this case, we could use regression learning, where we would minimize the error between the estimated image or the estimated measurement, and then through the forward model the known measurement, so that we can try to minimize the error between what we know to be a certain part of the state and the estimated image through the network. And now the network is constrained in some way, like, for example, as we saw in the NewNet, to minimize the feature representation of the image, and so we find the underlying features. This is commonly used in what's called variational autoencoders, for example, where we try to match the image to a probability distribution, and that's what's sort of indicated on the right here. This loss is called the Kullback-Leibler divergence, where we minimize the difference between the probability distribution for the estimated data or the return data from the network and the distribution of a known and a known probability distribution. And so through this process, we can find feature representations of an image or of data that may be more efficient for compression or for measurement or for improvement of the system. The third application is control, like we talked about with robotics, and here we would use reinforcement learning. So there's various forms of reinforcement learning, but basically we have some reward system. We have a way to evaluate the current state and a policy for what we want the system to do, and the network is trained to achieve performance against these constraints. So again, the structural features of the networks may be similar in these different examples, but the loss function and the goals of training are different, and we can achieve these different kinds of measurements. These lead to different architectures, so that we have the loss functions and control that we want a network to do, and then we lay out networks in a variety of ways. This is a sketch of a bunch of different neural geometries from 8 years ago, so there are more recent versions, but certainly, like the UNets involve autoencoders of various forms. GANs are generative adversarial networks, where you use networks to evaluate networks and can make recursive networks of various forms. So the network itself can be laid out in a variety of different ways. What I'm going to point to in the next several slides is just some examples of some very recent ways in which networks may be used in computational imaging. The first example is this neural estimation example. So with the deconvolution or the demosaicing network, we just used a very simple feed-forward convolutional network with a UNet structure. That works well, but of course, I'm sure everyone is aware of recent progress in large language models with ChatGPT, for example. The GPT part stands for Generative Pre-trained Transformer. So a transformer combines a feed-forward convolutional network to find features with densely interconnected networks that place these features in context. So, for example, in a large language model, you identify words, but then try to identify the words in context to understand their meaning in ways that allow you to adapt the reconstruction network to the nature of the word. For image data, this is much more complicated because it's hard to identify exactly what a word is, and so you have to find a way to break images into blocks, which is kind of what's shown here from this paper, of finding ways to find spatial and temporal features that you can then operate on with densely connected networks to identify the context of the feature and generate features then that allow you to use a decoder network to recover the image. So transformer networks for image processing can be relatively complicated, and in this case, for example, here we have a hierarchical separable video transformer. So the hierarchical part means you're looking at the video data on a multi-scale spatial temporal context, and so you have this multi-heads spatial self-attention network that's going to go and look through the video on various scales to find features. And then from those features, you need to regenerate image data, which is done here with this gated self-modulated feed-forward network. So the image processing systems can become extremely complicated, which allows them to find context and generate data with much more fidelity. We will not, in these series of lectures, consider networks of this scale of complexity because we're going to focus primarily on the physical system design, but we should be aware that after we settle on a physical system design, it may well be that building a large-scale transformer system to manage the image data will yield better results in image estimation. Beyond this, we began today's discussion with pointing to neural radiance fields. For purposes of our present discussion, the interesting things about neural radiance fields are that they use regression in training. The primary training mechanism is to train a network to regenerate known measurements and then use that network to interpolate new data. The standard model of neural radiance fields has been to look at objects from various perspectives and then generate new 3D perspectives from those known measurements, but this is basically a strategy for management of multidimensional data, and as we've discussed several times, the core problem in computational imaging is that the real world has more than 2 dimensions, but those can include not just 3 dimensions of space, but also time and spectra and polarization and illumination directions and so on. And so these implicit neural representations can be part of a strategy for using regression to interpolate data over multidimensional distributions, and this is really just beginning as a research field that will continue to develop over time. Now, Gaussian splatting, which we also mentioned at the start of today's discussion, is not a neural technique. It's a technique for creating 3-dimensional representations by creating features in 3-dimensional space that can be then used to interpolate new views. This is of deep interest because of the idea that, first of all, we don't represent measurement data as pixel maps or voxel maps. We can represent the data in ways that allow us to, quickly generate new perspectives on the data. But again, this then turns to a variety of different ways that could combine neural methods with other estimation methods in ways to manage large-scale multidimensional data that is still evolving and points to new directions in computational imaging. Another interesting sort of strategy along these lines is diffusion models, which instead of representing data as splots, takes data and represents it in noise distributions and then uses neural processes to invert the distribution functions of the noise to regenerate image data. This is often used to generate views that are not consistent with measurements, but that are plausible or useful ways to generate new forms of images in video. Again, we just bring it up here to emphasize the fact that image data representation, image processing is a very dynamic and evolving field, and its intersection with computational imaging will continue to be of interest. And so as we go through our understanding of physical design, we'll want to think about how we can apply these various interesting and powerful emerging image estimation strategies within computational imaging system. But that's the end of our discussion of image estimation strategies. It's time for us to start to talk about physical systems. And so in our next lecture, we're going to begin that with the oldest physical measurement system, which would be the pinhole camera, represented here from a 1755 edition of a text that talked about the camera obscura, where a small pinhole creates a projected image within a scene. This is a very, very simple physical system, but we'll find that computation plays an interesting role in ways to think about design of such systems. And it'll be interesting to us because it'll be our first example of creating a forward model and then analyzing the physical limits of measurement on that forward model.